if one puts inside a capacitor a insulator, it would become it's called a dielectric. You cannot put a conductor in it because the conductor would cause the charge to be discharged. But an insulator, for this purpose, is called a dielectric, and the capacity would increase. Kappa is called the dielectric constant. It's a dimensionless quantity. What it does, it increases the capacity. So C air is the capacity when it is filled with air. If you look into table 26-1, you would find a table of the capacity of the dielectric constant of the various material, and the kappa is always greater than 1. You might say that the vacuum, this should be actually a vacuum. The capacity for air is almost exactly 1. It's just a little bit different from 1. Why is there a capacity? There's a dielectric constant. It's because there are induced charges on the dielectric. Another concept is called dielectric strength. With a dielectric inside, if you now charge it, we have Q is equal to CV. If you now increase V, meaning increase in charges, when V is too large, it would cause a breakdown. There will be a discharge. And that magnitude of the V is called dielectric strength. For air, the dielectric strength is equal to 3 kilovolts per millimeter, which is equal to 30 kilovolts per centimeter. What that means is that if you have a condenser, if the voltage, if the inside is filled with air, if the voltage is larger than 30 kilovolts per centimeter, then it would spark, it would break down. Now in the ordinary outlet, you have 2 prongs. If the 2 prongs are maybe 1 centimeter apart, but usually it has only 220 volts, so it's not going to break down. But if for some reason you apply a tremendously large voltage across it, like 30 kilovolts across 1 centimeter, then they will break down. We'll come to the reason why it breaks down in a few minutes. We had used a constant epsilon 0. When you have a dielectric constant, all you have to do is replace K replace E0 by KE0, then every formula is correct. For example, if you have a surface charge sigma, the electric field usually is sigma over E0. Now this equation becomes E equals sigma divided kappa. So for the same charge on the plate, the electric field is smaller because of kappa. The one who studied the dielectric exhaustively and made the beginning great contributions to it was Faraday. At that time, the idea that the material, gas or liquid or solid, is always made of molecules and atoms was not yet generally accepted. So Faraday studied it as a kind of a homogeneous substance. Dielectrics, in his ideas, were sort of a homogeneous sort of material. But after people know that there are atoms and molecules, there is of course the question of, do we understand why there is dielectric? Why kappa is always bigger than 1? And then we find that there are two kinds of dielectrics. They are called polar dielectric and nonpolar dielectric. Polar dielectric consists of atoms which have a dielectric, which have a dipole, electric dipole in it. For example, water. Water molecule consists of oxygen and 2 hydrogen. You all know that the hydrogen are positively charged, the oxygen is negatively charged. That's because the hydrogen has a outside the electron, and in this bonding it gives part of that electron to the oxygen. So there's a net charge of negative on this in this region and a positive on this region. So that is a dipole. It's an electric dipole. So water is a typical polar dielectric. If you have a polar dielectric, if you put it between 2 plates, if you positive charge here, negative charge here, then every molecule inside of it has a tendency to arrange itself such that the positive is on top, the negative is in the bottom. So some of them would be exactly this way, others would be this way. There are a few that's this way, but overwhelmingly it is a more oriented with more negative on the top than at the bottom. So therefore what happens is that you have many of these molecules. You have this negative, positive, this is negative, positive, negative, positive, negative, positive. In the inside, it averages out. So if you take this layer from here to here, this one has a positive, this one has a negative. So they average out. The only place where it's not averaged out is on top. So at the top of the dielectric, there will be negative charges. At the bottom of this plate is positive charge. As a consequence, the dielectric produces the following effect, that it's equivalent, once you put the dielectric in, as far as the charge is concerned, you have one layer of positive charge, a layer of negative charge, a layer of positive charge. This is the original. In other words, the charge, the effective charge is reduced. So therefore the electric field inside is reduced. So for the fixed Q, this gives the Q. For a fixed Q, the electric field inside is reduced. If the electric field inside is reduced, the potential difference is reduced, because the potential difference is E times the distance. So the potential is reduced, and therefore if you take Q equal to CV, Q is the same, but now there's a reduced V, so the C is increased, and that is, C is increased by a factor of kappa. So that explains qualitatively why kappa is always bigger than 1. Does everybody understand what we said? You probably have learned this in high school. Now, in fact, one can calculate this. The idea that I just mentioned, one can go through in a calculation, and you can then compare the kappa that you can compare the reduction of charge that you calculate by this molecular idea compared with the experiment. How do you calculate? The most important thing is what we talked about there. The individual polar molecules would like to be orientated so that the negative charge is on top, positive charge is on the bottom. But on the other hand, it's not exclusively so. In fact, there are a few which are turned upside down. The distribution of how many is on top, how many is this way, how many is this way, follows an idea which is very similar to the Maxwellian distribution. That's called statistical mechanics. So statistical mechanics will tell you how the relative probability of the different orientations, and using that you can calculate the kappa. And this is the kind of thing which has been done in the 20th century, and it gives excellent agreement with experiment. How about the nonpolar molecules, dielectric? A nonpolar dielectric does not have a electric dipole. However, in an electric field, even a nonpolar molecule, suppose this is, there are atoms inside. There is no static average electric dipole for a nonpolar molecule. However, if you put an electric field in here, it has a tendency to drive the positive charge to the bottom and negative charge to the top. That calculation is more complicated, and it requires a quantum mechanical calculation. But with a quantum mechanical calculation, you can calculate the induced dipole, induced electric dipole. This is a little bit like what we already talked about. We had this image problem. If you have a conductor here and a charge here, then this side is going to be positively charged and this side is going to be negatively charged. So this sphere becomes a dipole, and that dipole is induced. And that is exactly the same idea here, except in this case it's an electrostatic effect. In a molecular case, it's a complicated quantum mechanical electrostatic effect. But there are theories about that, and that also gives excellent agreement with experiment. So in some sense, the quantum mechanical, statistical mechanical understanding of dielectric constant is in good shape. Gauss law with dielectric, you take any surface, there are charges inside, then E dot dA is equal to Q over kappa epsilon. Okay, let's do a few exercises from the book.第一步 of course 你立刻就看出来这两个是串联起来的，所以串联起来它的 equivalent 的就是 1 over 1/4加1/4，对不对？这是4 1 over 1/4加1 over 1/4再有一份是那这等于什么呢？这等于1 over 2/4等于2。所以这第一步就把这两个 reduce 成好，就变成这个是2个 microfarad， 这个是2个，这是2个，这是3个。这是3个。When you get to this, you may not know how to reduce it because the way it's drawn, none of them is either in parallel or in series. But this point 有4个线放在一起，你脑子里就跟4个电线接在一起。你当然可以把它稍微修改一下子，修改成这样，你把它变成。这个地方应该放一个电池，这儿放一个电池。这个跟这个没有分别，因为这4条电线连在一起，你把它这样弄一下子，当然还是连在一起。可是这一来的话，这一块就变成了一个并联的了，所以这个本来是2。这是2，所以就可以把这一块 当做是一个并联的，所以就变成了4，所以我就把这一块变成4，那就变成了什么呢？那这个呢，我又可以把它改成这样。你同意不同意？这个你这2点你可以连在一起，就变成这样。那好了，这一来这又变成，这上头是一个并联，底下是一个并联，所以呢就变成了很简单的了，就变成这样。方才这个是4，这是2，这是3，这是3。那现在这个4跟2是并联的，所以就变成6。底下这个也是并联的，也是变成6。那所以就变成了这就变1 over 1/6加1/6等于所以最后就得出来了。好，我们来做19P。19P 是这样一个，是这样一个图。这个30个 microfarad， 这个10个microfarad， 然后这个我们叫 C1， 这个我们叫 C2。然后呢，每一个都是100个 volt， 可是是倒着的，就是这个是正的在上头，这个是正的在下头。那我们先问有多少 charge， 是 Q1 等于VC1， V 是等于100个 volt，C1 是10个 microfarad， 所以这就等于1000个microcoulomb。哦，不对，这是1，不是10个 1.0， 这是3.0， 所以这是乘上 1.0， 这是100个 microfarad。我刚才弄，这是书上说这是1.0个 microfarad， 这是3.0个 microfarad。那么 Q2 呢 是等于 VC2， 可是是倒过来的，是等于100个 volt 乘上3个 microfarad， 所以这等于300个 microcoulomb， 可是是倒过来的。然后这书上说，你现在把这两个 switch 弄上去，事实上，你如果真是这样子的话，那要出很大的spark， 因为它这一下子，所以其实这里面还应该会加一个 resistance。当然，事实上所有的 wires 都有 resistance， 有 resistance 的原因就是它这 charge 以后，把那 energy 都 waste 在那个 resistance 去了。But anyway， 这个最后的 charge 呢，两个加起来的 charge 呢是 Q1 减去 Q2 减去 Q1， 因为 Q2 是300 Q1 是100，所以这最后的 charge 呢是200个 microcoulomb， 就是这个你把这 switch 弄上去以后，它这两个的 voltage 变成一样了，可是它 charge 不能够total charge 是 conserved。然后后来的这个 charge 呢，我们叫 Q2 prime 跟 Q1 prime， 那这等于 Q2 prime 加上 Q1 prime， 而这个 Q1 prime 呢是等于 V 乘上C1 是等于 V 乘上 1.0 个 microfarad， Q2 prime 呢是等于 V 乘上 C2 等于 V 乘上 3.0 个 microfarad， 所以你把这两个一加起来呢，所以就得出来200个 microcoulomb 是要等于4个 microfarad， 所以呢我乘上 V， 所以 V 等于50个 volt。所以在那情形之下，这两个现在都是正的了，正的在上头，负的在底下，不是 ，sorry， 正的在底下，负的在上头，因为这个 charge 大，这个 charge 小。那么在它们的分贝呢是1:3，所以是 Q1 等于50个 microcoulomb， Q2 等于150个 microcoulomb， 所以加起来是200个 microcoulomb。Positive on the bottom， 两个都是 positive on the bottom。Okay, I think we have learned everything there is in the book about the capacitors. We'll now go back to the method of images that I've discussed with you and do some more exercises. What we have done before is the following. If you have a sphere, you have a charge outside. First, do it for V equal to 0. And if it's not V equal to 0, the V is connected to infinity, it's grounded. If V is not equal to 0, you add more charge at the center to correct for example, the total charge. So the most important step is to take this to be V equal to 0. And the way to do it is first find its image. The image is such that if this is O, this is B, this is A, and OA times OB is equal to R squared. So since you know OA, you know R squared, you know OB. So you know where the image should be. And the next statement is that the ratio of the two, Q over 这一点我叫做 minus Q prime, Q over Q prime 的 square 是要等于 OA divided by OB. So you know OA, you know OB, so you know the ratio of the Q, and therefore you know what charge to put there. And the method of image tells you that if you have this Q and this minus Q prime, then it's guaranteed that this has to be equal to 0. And then the outside electric field produced by Q and minus Q prime is identical with the electric field for the case of Q with a conducting sphere at V equal to 0. So that's the method of the images. And what is the total charge on the sphere? There will be negative charges on here. Is equal to minus Q prime. We've proven that. But suppose what happens if you have a slightly more complicated problem? Suppose you have a charge here. You have another charge here. Answer. And this is a conductor at V equal to 0. You produce an image for this one, you produce an image for this one. So this is minus Q prime, this is minus Q1 prime. Each of the outside charge has an image, and the four of them together gives you V equal to 0 on the sphere. So, etc., etc. If you want to know, this is V equal to 0. If you want to know what is the total charge on the sphere, it's minus Q prime minus Q1 prime. This can even be a continuous distribution. If you have say a small bar of charge, then it has an image. So you can use this idea of images for the problem of a sphere. There are people who have studied whether one can generalize this, for example, to an ellipsoid, but without success so far. Now let us take another image problem which we have discussed. Suppose we have a charge here, and this is a half it's a half plane. This is a half plane， 是一个强基角，有这么一个 Q。那么 I have said what you do is this is Q, you put the image here minus Q, you put the image here positive Q, you put the image here minus Q. The electric field outside of the conductor, the method of image tells you, is equivalent to the electric field produced by these four charges. The original charge plus the three images in this first quadrant. 好了， let us now ask what is the So this is what the image method image tell you. Now I want to know what is the charge, total charge on， 比如说这点叫 O， 这点叫 A， 这点叫 B， on the surface， 这是 O， 这是 A， 这是 B， on the surface OA， 这个 charge 在这儿，这是一个 this is a half plane， this is another half plane。那么假如这 Q 是正的话，那这上就有许多负的 charge。We want to know what is the total negative charge. Obviously, the way you do it is you use Gauss law. 你 consider 一个 consider 一个 box. This side is just outside of this OA plane. This side is inside the conductor. So, total charge on surface OA 是等于什么？等于10。我们现在没有这个 no dielectric， dielectric is equal to 1， 乘上 flux out of这个我叫 figure 1， 这个我叫 figure 2， 这两个有关系，不是 different situation。我们用 Gauss law 在这儿 ，so therefore the total charge inside this by Gauss law is equal to 我们刚刚写下来的。Total charge is equal to E0 times the integral. The flux 就是 the integral. Now, 它是 out of 这个整个这种，可是在里 the electric field inside is 0， 所以你可以忘记掉，就只算外边的就够了。可是这外边这个呢，当然就跟这个一样，所以这就等于 E0 times flux out of plane OA in figure 2。为什么呢 ？Because figure A 跟 figure 1跟 figure 2的 electric field 是一样的。可是这个 flux 在这 figure 2里头呢，这个 flux 是 due to 4个 charges， 所以是 sum， 所以等于 sum of fluxes out of the plane OA in figure 2 due to the 4 charges。同意不同意？因为这个地方这个 flux， 因为这个 electric field 就是这4个 charge 所产生的，所以你可以把它这个 flux separately 算。E 是等于 E1 due to the first charge 加上 E2 due to the second charge 加 E3 due to third charge 加 E4 due to force charge， 所以每一个你 separate 算，所以就是这方面。好，现在要来算这个，比如说是这个 charge 产生了 flux， 那么这个 flux out of 这个 flux， 假如 Q 是正的话是 inside， 所以是一个 negative 的。不过问题是问从这儿出来这个 flux 有多少，所以我先画一个图。现在是这样一个东西。从这个地方，这等于这个 solid angle， 这等于 epsilon 0乘上 sum of the solid angle in figure 2 extended by OA at the 4 charges. 乘上 Q over 4 pi。因为这个 flux outside 的一个 sphere outside 的一点，它那个 flux 是 Q over 4 pi epsilon 0再乘上4 pi。4 pi 是什么呢？就是它整个的 solid angle， 那是 the whole thing。现在只有这一块，从这个 charge 所出来的这 flux 在这 solid angle， 所以就出了 sum of the solid angle in figure 2 extended by OA at the 4 charges， 这是每一个 charge。这句话现在大家懂不懂？现在先得要了解 solid angle 是什么意思。假如这是1，那么你在这儿有个空，这空就是这个 area。假如我现在是一个这是一个整个的 plane， 是一个 infinite plane， 那么这个它所 extend 的这个 solid angle 是什么呢？就是这个空张成了一个 plane， 那很显然是一半 solid angle， 就是2 pi。这个大家同意不同意？就是整个的 solid angle 是4 pi。你如果要用这个呢，你在这画一个 sphere， 这半个 sphere， 这个 radius 是1，这个 plane 在这儿，你这样画。整个它这个空就 extend 了 to 这个半个 sphere， 半个 sphere 的 area 当然是2 pi。所以 solid angle extended by a plane， 当然这个 plane 不能在那个 point 上 ，is 2 pi。假如是个 half plane 呢，那怎么办法？比如说这是一点， 这是一个 half plane。这是无限大，这样到无限大，可是到这儿是一个只到这儿为止。那所以你这个空是什么？就是这样。这个 angle 叫 theta。假如 theta 是等于派的话，这 solid angle 就是 2 派。那所以我说这 solid angle 是等于 2 theta。theta 等于0的时候，这 solid angle 也是等于0。那就是这个东西在我无限远的地方，那它根本不 subtend any solid angle。假如 theta 等于派，那应该是 2 派，那这 formula 是对的。所以现在 for a half plane， 好了，咱们用了刚才这2点来回到本来的那个 total charge on OA in figure 1等于epsilon等于 q over 4 pi of S1 减去 S 加上 S2 减去 S3 减去 S4， 我得要跟你讲这是什么意思。我们现在是要问 the total flux due to 这个加 due to 这个 separately 来算，所以先算这 total flux due to 这第一个。那么这个呢，我这刚才想画出那 theta 是什么意思呢？你从这儿发出去的是这样。这个 angle 叫做 S1， 因为从这儿出去的这个 flux 都在这个 half， 这是一个 half plane， 这是一点，所以这个 angle 这就是刚才我所要想做一个 half plane subtend 多少angle， 那么这个呢是 S2。这个呢是 S3， 这是 S4， 每一个都是 the solid angle subtended by 那个 half plane OA 在这4个地方。为什么有的是正的，有的是负的呢？因为我们这assume 是这事实上讲起来应该是整个是负的，因为 S1 是假如 Q 是正的话，它是向这面去的，而 S2 它这是个负 Q， 所以也是向这面去的，所以呢这两个是同一个 sign。这个跟这个它的 sign 呢是负 S， 因为这个 S3 这是一个负的，所以你从这儿射到这儿的话，它的 charge 是这样的。它假如 Q 是正的，它的这个 field 是这样的，所以是负的。所以你去想一想，是这样的。 可是 S1 等于 S2 obviously， 所以这个等于 minus q over 4 pi。 S1 等于 S2， 所以是两个 S1。 S3 等于 S4， 所以等于 minus 两个 S4。可是我们用刚才的 formula 说是 S 是2倍的 theta， 所以就得出来 minus q over 4 pi 乘上 2 乘上 S1 减去 S4 which 是等于 minus q over 2 pi 乘上 2 theta 1减去2 theta 3 2 theta 4。可是 theta 4你看这个图的话theta 4加上 theta 1等于派，所以这东西等于 minus q over 2 pi minus q over pi 乘上pi minus 2倍的 theta 4。theta 4就是这个 angle， 就是这个 angle， 这个 angle 就是 theta 4。所以现在我们得出来，这是等于 total charge。比如说是，假如说是 theta 4等于45度，假如它正在中间。那么 2 theta 4就变成90度， pi 减去 theta 90度就是 pi over 2， pi over 2就出 minus q。 If theta 4 is equal to 45 degrees is equal to pi over 4， 那么 total charge 等于 minus q over pi 乘上 pi over 2等于 minus q over 2。所以如果它是在45度的地方，这个在这上的 charge 就等于 minus pi q over 2， 在这上的 charge 也是 minus q over 2， 所以在这两个的 charge 加起来是 minus q。 这个我们上回已经证明了，因为你如果把这个整个放在一起的话，它没有 total flux， 所以这个 q 的 charge 一定要被这样两个 compensate。在45度的时候，这个就是 minus q over 2， 这是 minus q over 2， 所以这是正确的 formula。What is this is a 就巧用了 method of images， 不过这个的唯一有个 concept。是 it's when you first see it you have some you may have some difficulty, and that is the meaning of a solid angle, and in particular it's how do you calculate the solid angle subtended by a plane。 再一点这个是很简单，是 2 pi。 How about by 一个 half plane？ half plane 那就是用刚才那个是 2 theta。Okay. Since I did not assign any exercises of chapter 25, so we'll now do a few of the exercises of 25 of chapter 25. And for the final examination, I considered that we have covered chapters 1 up to the end of chapter 26. you will start from chapter 27 next semester. P 比如说是 29p。There's a charged rod here with a density of charge equal to Cx. So there's no charge density here. The charge density linearly increase until you reach the same. The question is to calculate the potential at V. To calculate the potential for 这种问题的话 you always consider V to be equal to 0 at infinity. Then the V due to a charge is equal to charge divided by 4 pi epsilon 0 times R. So this is equal to 1 over 4 pi epsilon. 这一小段一小段算 integral 每一小段是 Cx dx. 这是 total charge 在 dx divided by r 是这点是 x 这是 r 是 x squared 这等于 8 pi epsilon 0 c dx squared. From x equal to 0 到 x equal to L. dx square 是等于 2x dx, 所以跟这个 8小的，所以这等于 c over 8 pi epsilon 0， 这个是等于2倍子的 square root x square 加 y square from x equal to 0到 x equal to L， 这等于 c over 4 pi epsilon 0 of square root of L squared 加 y squared 减去 y。Number 47p says there are 2 electrons with charges minus e, and there's a third electron at the point, so there are 3 electrons. This electron 走到 infinity， 这两个不动，这走到 infinity。问它的 velocity 多大？这个非常简单，这 conservation energy。这个原来这两个是不动的，所以原来的 energy original energy 等于 original kinetic energy 是 0。因为原来是不动的，加上 original potential energy，original potential energy 是有2倍子的，一个是这两个，一个是这两个，乘上 e squared over 4 pi epsilon 0 d， 这要等于 final 的energy。final 的 energy 呢 potential energy 没有了，因为这个 R 是等于 infinity， 只有 kinetic energy， 所以是1/2 mv²。所以你把这两个消脱就得出来了 v。potential V due to a uniformly charged shell。假如这是个 shell， 我问他 V 是什么？这 outside 在这一点 ，P 在这一点 ，outside V 等于，那就等于 because the electric field is the same as if the whole charge is concentrated in the center, so it's equal to Q over 4 pi E0 1 over R。 所以我把它 plot 起来了，这是 V， 这是R， 这一点是 R， 这个 radius 是到 inside 的话呢 there's no electric field, and that means 所有的 potential 是 identical inside V 等于 V on the shell， which 是等于 Q over 4 pi epsilon 0 1 over R， 所以在里头是这样。在这儿的 derivative 是 zero， it should be because according to the shell theorem electric field is zero。 在这儿它的 derivative 是 negative， 所以有个 positive charge outside， 假如 Q 是正的。这题目是有两个 sphere， 这个 sphere 是 R， 这个 sphere 是 2R。 在这个地方，这个 V 它的这个 potential， 它原来这个 charge 是 Q， 这儿的 charge 是等于0。原来这样。现在问问，假如把这两个连起来 ，problem， if the two spheres， 这两个 metallic sphere，if the 每一个就等于是一个 capacitance，if the two spheres are connected by a wire, what is the charge, the final charge distribution?原来的 total charge 是 Q plus 0等于 Q， 问后来是什么一个 charge？ 所以假如后来的 charge Q1 prime and Q2 prime, let Q1 prime, Q2 prime be the final charges. Then Q1 prime 加上 Q2 prime 就要等于原来的 Q， 而 V1 prime 等于 Q1 prime divided by C1， 而 V2 prime 要等于 Q2 prime divided by 这是 2C1。可是这两个调相等，所以 Q1 prime over Q2 prime 等于 C1 over 2C1 等于1/2。所以 Q1 prime 是等于1/3个 Q。Q2 prime 等于2/3个 Q。I have to be away next Monday. So I have asked赵忠贤 to take over for the Monday lecture. 赵忠贤院士是物理所的重要的院士，他的最专长是叫做高温超导。高温超导 is one of the hottest subjects in physics for the last 15 years. In 1986 and 87, there was a great event in physics research. Namely, people found that they are superconductors at approximately 100-degree absolute. Before that, no superconductor has been found with a Kelvin temperature over 23 degrees. So suddenly the temperature become very high. So that's why it's called 高温超导. Actually, of course, it's 非常低温的. 100 degree Kelvin is still extremely low temperature. But from the behavior of superconductivity, it was a very peculiar thing. And after that, all these in the last 15 or 18 years, over the world, there are lots of very important research. Today, the situation is as follows. There are a number of applications, and I think Zhao Zhongxian Yuan will tell you some of these applications. But the fundamental reason, the mechanism for 高温超导 is not understood. Here at Tsinghua, there are a few theoretical research workers specializing in this field. But there must be hundreds of theoretical research workers about the mechanism for 高温超导 active today all over the world. But the basic mechanism is not understood. Because the basic mechanism is not understood, it is not clear whether one can push to higher temperatures, and it's also not clear if you want to look for material which would have higher temperature superconductivity, higher than 130 degrees Kelvin, what kind of material would you look for? Because you don't understand the mechanism, so therefore there's no guidance about what to do. So in the last 15 years, many experimentalists tried various things, and from time to time they hit upon something which unexpectedly is a high temperature superconductor. So it is a very active field, still developing, but the fundamental problem has not been resolved. And in China, there are people both working on the theoretical aspect and experimental aspect and the application aspect. So I'm sure you'll learn a lot from next Monday's lecture. I'll be back next Wednesday. Okay, bye-bye.